Yeah, so we start from the recording. So as I said, so I'm Leonardo Banchi from the University of Florence, and it's a pleasure for me to share the first session. So we have now three great speakers. So the first one invited talk and two contributed talks. And so I want to also remind you that so you can type your questions in the Q&A button in Zoom, or you can also raise your hands and then I will tell you when to speak. So all the unanswered questions, so of course we have some limited time, so we cannot answer all the questions. So all the unanswered questions, then you can ask them directly on Slack. Okay, so with this, it's a pleasure for me to introduce Min-Hsiu Hsieh from the Honghai Quantum Computing Center in Taiwan. So, and he will talk about the power of quantum neural networks. So please go.
Okay, can everybody hear me fine? Good. Okay. So it's my great pleasure to be able to speak here, and I would like to thank the local organizer for this wonderful conference and let me speak. My name is Min-Hsiu Hsieh. Right now, I'm the director of the Honghai Quantum Computing Center in Taiwan. And today I'm going to kind of like give you an overview of what we did on using quantum neural networks in the past few years. So before we dive into the topic of quantum neural networks, let me remind you why quantum computing matters. Why do we care about quantum computing? So it all starts with this very nice figure, that this complexity rule. We all know that this is famous question P versus NP, and we know that P can be generalized to bounded probabilistic polynomial class. That this class BPP is believed to be like whatever problems that lies in BPP means that this kind of problem can be efficiently solved if you are given a classical computers. And then when we have a quantum computer, we can naturally generalize the definition of BPP to BQP, which is this purple circle. And a lot of effort in the past 40 years is trying to understand the boundary between BQP and BPP. BQP are the class of problems that believed to be that can be efficiently solvable if you are given a quantum computer. So we're trying to identify what kind of questions that can be solved using quantum computer, but that would be hard given just a classical computer. And we know that Shor's algorithm is believed to be an example that lies outside of BPP and lies inside the BQP. So to summarize, it is an interesting question to identify the boundary between classical computing and quantum computing. So if we narrow ourselves to machine learning, we can ask similar questions, and these are the questions that I would like to answer if we have a quantum neural network versus classical neural network. Okay, so this is a quick summary of machine learning. So machine learning basically is this. So given an unknown function with input space X and output space Y, you have no idea what this function looks like. All you can do is that you're trying to estimate this function using this training data. So given input Xi, you get to observe Yi, and there are a collection of like n examples. And then with these n examples and probably some knowledge of your hypothesis set, which is the collection of all unknown functions, you're trying to design an learning algorithm that hopefully you can estimate, like give you a rough idea of what this unknown function looks like. And for example, the example of this hypothesis set could be, for example, a collection of all Boolean function or collection of the projective function, etc. And from here, you can see that there are two types of machine learning questions. The first type of question is belongs to design an efficient learning algorithm, and it's called the computational complexity, trying to characterize the efficiency of your learning algorithm. The second type of questions is called the sample complexity type of questions. So the idea here is trying to understand how many training data you need for you to get a good estimate. So you don't want to have too many observed data before you can output this function f hat. So what is the proper size of the data is another important question. And normally the mathematic tool used in the sample complexity are concentration, inequality, and all that. So it has a type relationship with statistic. Okay, so moving forward to the content machine learning. So there are 4 different categories depending on the type of inputs and as well as type of algorithms. So there are 2 types of inputs, classical input or content input. And then there are 2 types of algorithms, either the algorithm that can be run on the classical machine or the content algorithms that need to run on the content machine. So if you have this 4 different selections, then you will have these 4 different categories. CC means that the problem the input are classical data and the algorithms are classical. And then QC, CQ, QQ. These 3 other types show up, emerge because you have a content ingredient. Okay, and then QC. This normally QC. Let me move on to the next slide. So normally QC includes, for example, state demography or content control. In this case, the input content system, right? And then you can somehow extract partial information without disturbing your content system. And then you can post-process this partial information using classical post-processing. And combined with machine learning, you can feedback to your control system, and then you can do the next round of content control. State tomography can be also put into this framework. The input is a content state, and you're trying to kind of characterize the element of your density operators. There are more varieties in CQ question, and actually the big companies nowadays that works on QC, they really want to push the improve the classical machine learning task using content algorithms. So the problem here is, for example, this linear equation solvers, HHL algorithms, perceptrons, recommendation systems, trying to speed up the semi-definite programmings, and etc. So so this CQ type of questions now actually play a major role in quantum machine learning. And then this final categories, probably less, fewer people working in this domain. In this case, that the input is content and the algorithm is also content. So an example would be maybe to identify whether a given content state contains entanglement or not. So we will have an example for that later. Okay, so if you have this hybrid categories like either CQ or QC, this kind of questions always involve this reading. So because for the CQ questions, the inputs are classical, but the algorithm are content. So the first step you would have to do is that you have to encode this classical data into some content state. And then you processing using some content device, for example, IBM Q or Google processors. And then finally, you would have to read out. So the task won't be done just giving you a density matrix, because what we really need is the classical description. So from this this diagram, you could see that the bottleneck of the current quantum machine learning there are two bottlenecks. The first one would be the reading question. So because right now there are no efficient general quantum algorithm that can guarantee that within certain t-step or like in logarithmic to your input dimension that you can encode a quantum, encode a classical data into a quantum system. So reading is a major bottleneck. Likewise, readout is another major bottleneck because let me move on. So for the readout, the only known solution is the state tomography. And in general, state tomography require this many copy of measurement or this many copy of the state. Here, D is the Hilbert dimension of the Hilbert space that your density matrix live on. And R is the rank of your density matrix. So this is kind of optimal. So you won't be able to have anything more efficient than this. So from here, you can see that even though you have an efficient quantum algorithm, but if you want to read out the classical description, then all the efficiency will be kind of like destroyed by this final state. With my student, we kind of noticed that in general, in the machine learning questions, the input output have certain relationship. So it's not, so the output is not completely unknown. So in this case, so we show that if we can, if the output matrix V lies in the row space of the input matrix A, capital A, then if your quantum computer generates this pure state Kate V, there will be an efficient readout algorithm that only require R copies of V, and this R is the rank of the matrix A. In this sense that we can like get rid of the dimension D that this density matrix lives on. And I find this very interesting. So if you would like to know more detail, the reference is here. Today I won't be able to go into the detail for that, but if you feel like to know more, we can chat offline. Okay, so those are the two bottleneck, read in and read out. Now I would like to move on to the neural network. So I believe the participant in this conference would probably knows neural network quite well. So on the left-hand side, this is a classical neural network. The first layer is you can think of this is the feature extraction layer. So given classical data, you extract the necessary feature, and then you put those data into a neural network. So and the idea is that we're trying to optimize to train the weight between the nodes, and you can use this back propagations or classical gradient descent to update this weight so that it converge to so that you would get the right weight. And this kind of idea has been generalized to that I so-called QNN. So you can have a state preparation unitary that depends on the classical input, and then instead of the neural network, you use parameterized quantum circuit, and this quantum circuit basically consists of rotation gates. So it's either rotation along X, rotation along Y, rotation along Z, and you can adjust the angle of the rotation. And then of course that it accompanies like CNOT gates in between those qubits. And then the classical optimizer are similar to the classical neural network. You can use gradient descent methods, or like gradient-free update rule. Both are fine. Okay, so once you have this kind of picture, so you have either a neural network, and the next question that you would like to understand would be the boundary, like what is the power of classical neural network versus the power of quantum neural network, right? And in the machine learning communities, there are 3 theoretical questions that people are interested regarding those learning models, and neural network is one of them. For example, those 3 questions would be the expressibility of your neural network, the trainability of your neural network, and the generalization of your neural network. And I will go through this one by one. Okay, so the expressivity is defined as follows. So we want to know that how the architecture property of a neural network would affect the computation, the resulting function that it can compute. So so based on this, my student and I and myself, so we investigate the expressive power of a quantum neural network versus a Boltzmann machine. So we show that the circuit we use here is the EOS layers of tunable quantum circuit, and in each layer you have many CNOTs. So basically, between any 2 qubits, there will be a CNOT connection. So it generates entanglement very quickly, long-term correlation very quickly. Within just 1 block, it could already generate all kinds of like entanglement within this input qubit. And we show that if we benchmark the computing power using the diversity of distribution, so we want to show that what kind of distribution that this tunable quantum circuit can generate. So the diversity of distribution that it generates would be the benchmark. Okay, and we show that this kind of tunable circuit can generate more type of distribution than general Boltzmann machine. And I also believe that people in this participant in this community knows what general Boltzmann machine. So basically, you have visible layers and hidden layers. Other than link between these 2 layers, there are also connectivities between within each layers, within either hidden layers or visible layers. So this kind of quantum neural network can generate more distribution than general Boltzmann machine. And then the general Boltzmann machine can generate more distribution than this tree-type quantum neural network. So tree-type means that in the first layer, you only have like nearest neighbor entanglement or CNOT. Only at the last layer, you have long-range correlation. Okay, and this kind of tree-type neural network can generate more distribution than the restricted Boltzmann machine. So this bottom 3, it's actually quite easy to see why this is true, because this general Boltzmann machine can generate long-range correlation fairly quickly. But this type of circuit can only generate long-range correlation at the last step. So this could generate much more rapidly and fast. The more tricky part is to prove this type of QNN have more generating power than this Boltzmann machine. And the idea is to go to this IQP circuit. So IQP circuit, if you know what that is, it has been proved that under certain complexity assumption, this commuting gate can generate more distribution than any classical method. And we can show that any IQP circuit within constant overhead can be simulated by this kind of quantum neural network, and that's hence that this has more power than this. So it's by reduction. And so those are the results that to compare the expressive power. Nowadays, if you look at archives, there are more way to benchmark the function that different type of network can compute. So the size of the distribution that you can generate, just one of the benchmark. You can pick other benchmark, and there are a few results in the literature already. Okay, then we move on to kind of like understand what the learnability of the QNN is. Here, the learnability can be defined as the trainability plus generalization. So trainability is defined to be like how easy it is to find the appropriate weights of your neural network given the data. In 2018, the Google group shows that actually train a quantum neural network would have this Barron-Pareto problems. So basically, you can see that the gradient would vanishing. The gradient would vanishing exponentially with respect to the number of qubit. So the gradient vanishing very quickly. So the catch is that they use the fully connected CNOT in each layer, and then they randomly select their rotation gate, and they show that in this case the gradient would manage fairly quickly. And then my students, with my student, we show that if you have some like tree structure, in this the tree structure means that you only have fewer CNOT connectivities, and if under this case, the gradient would not vanishing exponentially fast. It only vanishing proportional to the number of qubits. And so actually there are, again, because quantum machine learning is a very hot topic, and there are many results toward this similar question. So for example, Patrick Cole from NIST, his group has generated many similar results in this domain. For example, they look at, let me go back here. Sorry. So they look at the local observables. So they also show that if the observable is local, the gradient would not vanishing exponentially fast. And there are also other ways to arrange this kind of CNOT connectivities, so that you can relieve the Barron-Pareto's phenomenon. Okay. So we also have some generalization in this domain, and you can take a look at this paper with Kaining, my student. The next we study the trainability of QNN in a more restricted setting. So we use empirical risk minimization framework. So in this case, so normally if you use ERM, the basic idea is that you don't know the true data distribution. So instead you use empirical distribution. And here we kind of like using the quantum circuit, Turing quantum circuit to generate yi hat. So this is, and then the loss function is the mean square loss function. What is slightly different is that here we include this regularization term. So you can choose a L2 norm as a regulators. And then we show that we under this ERM framework, we look at two quantities, two utility bounds. And if you are from classical domain, like these two utility bounds are also very common in the classical literatures. The first utility bound is just look at the gradient, the variance of the gradient. And then the second utility bound measures whether you would converge to your global minima. So theta star is the global minima. And T is the number of iterations in the machine learning term, it's called like epoch. So how many iteration or epoch? We show that for this gradient, the variance of the gradient, it's actually upper bounded by these quantities. Again, sorry, D here is not the Hilbert space of your content system. D is the size of your parameters, so parameter space. And because we can also, because nowadays the quantum circuit has error. So P is the errors that your quantum circuit, the error rate of your quantum circuit. T is the number of iteration, LQ is the circuit depth, and K is the measurement, the number of measurements that you use in order to extract the statistic for the classical optimizers. So somehow we show that with this regularization terms, you would also you won't observe this Pareto phenomenon in this case. And then we can also show that the convergence to the global optima can be guaranteed. And it also depends on these parameters. Like if you have more measurements, then of course, then you can get the statistic betas. And then you could have a better utility bound, this R2 bound. Okay. I might want to, so the generalization, basically we study this statistic query algorithm, this statistic query models. We show that they can be efficiently simulated by QNN, but I would like to kind of skip this slide because it would take me too long to go into the definition of statistic query and all that. So just if you are interested in this, we can discuss offline. Okay, so so other than these three theoretical questions regarding a QNN, here we also look at two applications. So the first application is in this QQ domain. So the input is content, the algorithm is also content. So in this domain, I kind of like questions in this domain because then you don't need to justify the reading question or the readout question. So everything becomes quite natural. So we look at this entanglement test question. So entanglement test question basically asks for given state, is it entangled state or not? Okay, so this is the question of entanglement test. And so we in the paper we have a more general algorithms that use matrix multiplicative updating algorithms, and we also have a NISQ algorithms that you can just use quantum neural network to implement that. So and with that kind of settings, Jianwei Pan's group, they actually can carry out the experiment for us. So I will show you some experiment data here. So the idea we have is that we use this quantum generative and adversary network idea proposed by Seth Loy in 2018. The basic idea here is that in the quantum regime, the loss function can be easily modeled by error probabilities. So let's take a look at the figure. So this content generative and adversary network looks like. So basically, this is a two-player competing games. The idea is that you have a player that called generators. The idea of generators is trying to generate something that is close to your given data. And the discriminators, the goal for the discriminators is trying to distinguish whether the input to it comes from the given data or the data generated by the generators. So it's like these two parts, generators and discriminators, they are competing with each other. Okay. And in this case, a natural benchmark is like just the success probabilities, right? Either it's from rho or it's from G, U rho or from UG. A nice observation that made by Seth Lowy and his collaborators is as follows, because this loss function success probability is linear in sigma and this two outcome measurement. And also notice that the discriminator, like the collection of POVM or general measurement, it's also form a convex set. And the generators, the set of content state also form a convex set. And in this case, so it's a minimax question and the domain of minimax are convex, the function is linear, then it will be efficient to go to the equilibrium state. So Seth Lowy, they make these observations, and they say that this content generative and adversary network might have advantage versus might have content advantage over the classical generative and adversary network. And we actually demonstrate this idea using this entanglement test, using the task of entanglement test. So these are the experiment result. So if the given state U rho is separable, so it means that there is certain in the labs there is this unknown machine that generates this rho, and rho is separable. We can show that if you look at this purple line, our experiment demonstrate just within 14 iterations, you can reach to the equilibrium state. Here, the equilibrium state is the 1/2 success probability. Why 1/2? It's because the discriminator cannot discriminate the data, whether the data comes from your the given device or it comes from the generators, because the generators can generate the exact state. So that's why the discriminator is more like have a random guess, and so the equilibrium success probability is 1/2, and you can see that it's a fairly quick. It converges to the equilibrium state fairly quickly, only 13. And then here the fidelity. So the fidelity here compare the generated state versus the given state, and we can show that the generated state would becomes the given state with like fidelity 1. So it's basically the same state. On the other hand, if the given state is entangled state, you can see that it never goes to the equilibrium if you continue the experiment, okay? And the fidelity, so because we restrict the generated state, it won't be able to generate this entangled state. So the fidelity would be bounded. And this is how we can use this kind of idea as the entanglement test. We can say that after a certain iteration, if it does not converge to the equilibrium state, then the given state contains entanglement. And this experiment using quantum optics helps us to verify that. Okay, the second application here is the error we can use it for error mitigations. So how do we do that? So recall that in the previous slide, basically you have a loss function and you use gradient descent trying to locate the optima theta, like optima angles in your circuit. Here we include all possible architecture. So this small a is all possible architecture, and trying to optimize over all possible architectures. So what are the possible architectures? Here we can say that, for example, if your single qubit gate contains these 8 elements, Rx, Ry, Rz, so these are tunable, identity, T gate, Z gate, Y gate, X gate. So there are 8 different choices. And then you also have 3 different type of control unitary, control X, control Z, and just did nothing. If you include all the architectures, trying to optimize all the architectures, then you will see like the benefit why we want to do that. But the first question that you would observe is that the search domain would grow exponentially with respect to the number of input qubits and the depth of your circuit, because we have 8 and you have n qubits, so the possible solution is a to the power of n, right? And this is another 3 power of n, and then you have the circuit depth L. So the search space will become unaffordable very quickly. So this type of question, so we got this idea from this classical architecture search, and we actually can kind of borrow some ideas from that domain as well. So we can use kind of, for example, weight sharing. So even though the possible architecture is like grows exponentially with respect to the number of qubits, but somehow if 2 layers have the same if 2 layers have the same circuit, we do not update. So we share the same weight. In this case, it reduces the number of parameters that you have to optimize. So this is called the weight sharing strategies. But weight sharing strategy create additional questions. For example, you would not converge to the global minima as fast as you don't use weight sharing. Okay. So this is like a picture to kind of like illustrate the steps. But let me give you some numerical idea why this content architecture search would give us very, like one of the best error mitigation performance. So we pick kind of like a very kind of toy model. So this is hydrogen like H2, and then we express the Hamiltonian. We expand the Hamiltonian using Pauli basics, and the goal is to compute the ground state, the lowest energy of this molecular. So we did the experiment. So if you look at this subgraph C, the red line is the, sorry, oops, stop. So the red line, I will be finished this talk with 2 more slides. So the red line is the ground state, so it's minus 1.136. This is the minimum ground state. And if you use the IBM simulators and assume that there is no gate error, you can see that the QNN would converge to the ground state roughly in less than 40 epochs or 40 iterations. But if you if the gate contain noise, suddenly the performance will become very, very bad. So this green line is assume that the gate contains gate noise, and you see that the ground, you can only estimate the energy above minus 0.4. Then if we look at our using this content architecture search strategies, we demonstrate two, so this E is just another parameters that I did not specify, but just look at the most simple case like E equal 1, right? If you use this architecture search, we can actually get to the ground state that is close to minus 0.9. And if we somehow increasing this, we call supernet, from 1 to 5, we can get the ground state energy that is fairly close to what you want. So you can see that there is a big improvement if you use quantity architecture search. So you search the best architectures using your neural network. And the same idea could also somehow overcome the Baron-Pareto phenomenon. So this is this brownish line is the standard content neural network, the gradient of content neural network, and you can see that the gradient decrease as the circuit depths increase. But if you use our content architecture search, like search the optimal architectures in each iterations, somehow you can improve, you can jump up your gradient. So it's not as bad as this. So it also helps us to eliminate the Baron-Pareto phenomenon. Okay, so basically this talk is kind of like going over many of my results, and right now we have like almost 10 plus papers in this domain. So if you find that interesting, feel free to let me know. Okay, thank you very much.
Okay, thank you. Thanks a lot for the wonderful talk. So we have time for a couple of questions. So please write your questions either in the Q&A part or just raise your hand. Okay, so I see there is a yes. So Jonas Kubler.
Yeah, hey, thanks for the talk. Nice overview. I have a question concerning the expressibility of your network.
Okay.
So let's say intuitively, if I don't have any idea where the optimal state lies in the Hilbert space, then I would kind of assume that I need exponentially many parameters to parameterize this whole space and then to eventually find a solution. Or is there any reason why there's only, like, why should polynomially many parameters suffice or something like that? Could you comment?
So I think what we show here is slightly independent of your question. So we do not, we benchmark the performance using the diversity of distribution that this different type of network can generate. So we do not actually look at compare the parameter space here.
Okay.
Yeah. But somehow but in order to make a fair comparison, the parameter space between this the top quantum neural network and general Boltzmann machine are somehow the same. So basically, we fix the number of weight. So the number of weight in these two graphs that are roughly are the same.
Okay.
Yeah. So it's not like we compare exponential space, parameter space versus like polynomial space.
But for example, in your hydrogen example, like what you showed at the end, like you would kind of have to ensure that like your parameterization can actually parameterize the ground state, right? And
yes. So so I think this is kind of like the standard trick in quantum chemistry nowadays. So if I say something stupid, please point that out, because I'm not an expert in quantum chemistry. But what I understand is that basically you can go through this second quantization, and then goes from the normal Hamiltonian and rewrite that using polybasics. And this will give you a fairly accurate description of your original, like this, in this case, hydrogen systems. And this same strategy has been used in, for example, Google's recent science paper. So they're trying to simulate 12 hydrogen atoms using their cyclomo quantum processors. So basically, they did the same steps. They convert that to the Hamiltonian using polybasics. Did I answer your questions?
I mean, I think I kind of get that part, how you arrive at this Hamiltonian, but then like the question is, you can only optimize, say, polynomially many parameters in the number of qubits that you have, right?
Yes,
so you kind of have to neglect some part of the Hilbert space.
Okay, then
yes,
sorry to
that's
interrupt,
right.
but maybe it's better then if you could continue the discussion on Slack, just to check whether there are. I mean, is there another quick question from the audience?
May I ask a question?
Yes, sure.
Sorry, I don't find the channel at Slack. So when you plot the gradient norm, are you doing an average over all the parameter space, or when you have shown the evolution of the gradient norm?
Sorry, it's I did not get the question. So are we using what?
So you have somehow claimed that your meta learning method to learn quantum circuits, this it's so that the gradient norm keeps up.
Yes.
Do you average this norm over all the parameter space, or?
Yeah, so we normalize this norm by the dimension. So so they are so it's gradient norm divided by the dimension of the system here, and so that we kind of get rid of the dimension. We only focus on the depths.
Okay.
Yeah. Okay, so thank you. Let's thank the speaker. I think it's time to move to the next talk.
Thank you. I will stop sharing. Okay, good. Thank you very much.
Thank you. So the next talk is by Matias Bilkis. So please, Matias, can you share your screen?
I will. Can you see my screen now?
Yes, I can.
Great. Let me put the full screen.
Okay, so great. So it's a pleasure to welcome Matias Bilkis from the University of Barcelona. And so he will talk about variable Ansatz VQE, a semi-agnostic approach. So please.
Okay, thank you very much. I am Matias again. I am from Autonomous University of Barcelona, and I am going to present a work that we are kind of about to finish and push to the archive soon with these amazing people, which are from left to right: Guillaume Verdon, Lucas Cincho, Marcos Erizo, and Patrick Coates. So we all know that quantum computing holds the promise to solve classically impossible to solve problems. But the question is, what can we do now in the present with noisy intermediate scale quantum devices? And it is not very clear whether we will be able to use such devices to do something or not in the short term. So For instance, there are a lot of trainability issues that the last talk about, for instance. So one of the best hopes to make use of those NISQ devices is to go for quantum machine learning. And quantum machine learning trains the parameterized quantum circuit using one or more input states. So to minimize the cost function that has this form, where O is I are operators, U is the ansatz of the parameterized quantum circuit, and rho I are the input states, and F some function. So for instance, if we are doing VQE, the cost function reduces to the energy of some state that we are preparing associated to some Hamiltonian. This parameterized quantum circuit is often known as the ansatz that we use, that in general we can express as a product of single qubit rotations and entangling gates. So I would like to notice that in my notation, I am using K to denote the structure of the ansatz and theta to the continuous parameters that are, for instance, associated to single qubit rotations. So the way that the quantum machine learning goes is to compute this cost function. So to in using our current classic quantum computers, and minimize this cost function by leveraging the power of classical optimizer. So it is not clear if we will be able to use this idea to minimize this cost function due to trainability and noise issues. So for instance, if we have a noise, the cost function estimation is degraded, and also it has been recently shown that training these variation algorithms, for instance, is NP hard, and the problem itself, of course, depends not trivially on the ansatz that we choose. More on this is that we have this barren plateau issue that has recently been talked about, where the gradient of the parameters exponentially vanishes, and this leads to untrainability. A comment on this is, well, people like to show landscapes here. So for instance, if we are putting the optimizer into a barren plateau landscape, it will be very hard for it to find the optimal solution. Whereas if we put it in a better landscape, it will be easier and it won't get stuck. So furthermore, the problem that arises is that even noise induces barren plateaus. So if it has recently been proven in a paper by Samsung Wang and more people at Los Alamos, that in the presence of noise, barren plateaus appear. So where does our work stands? The idea is that the structure of the ansatz is very important for the success of quantum machine learning in general, whether we will find the minimum of this cost function or not. And if we use a very expressible ansatz, we will be in the presence in general of barren plateaus. Whereas if we use a very shallow one, we just won't get the target state that we aim for. So even more in the presence of a hardware noise, we do also find barren plateaus in general. So these are very nice and exciting times to design new algorithms. So the outline of my talk is first to talk about some ansatz that people use, and in particular in QE. And then talk about our results. Sorry, it's missing some point here. So I'm going to present the ansatz and then our algorithm, then some results, and then conclude. So when doing BQE, and now I am talking on variational quantum mechanics solver, one usually finds one can discriminate between two strategies to create ansatz, where one uses a fixed structure or a variable ansatz strategy. So for fixed ansatz, we may devise a hardware efficient ansatz, which is problem agnostic and has this brickwise structure of single qubit rotations and neighbor entangling gates, and this is repeated all along the circuit. And of course, this is well, one can see that this is a very expressive ansatz, and there is no overhead to implement this with native gates. That's why it's hardware efficient. But the problem is this that this is often too expressive, leading to variant atos. Also, well, and in particular when randomly initialized. And then we can devise some more problem-inspired ansatz like QAOA that I got here, or unitary coupled cluster, which is used for quantum chemistry purposes, and is inspired on quantum chemistry methods. So in general, again, they are inspired for that problem, but they lead to very deep circuits, and this will often suffer from hardware noise. So there has been plenty of work recently on constructing variable ansatz structures. So for instance, there is Adapt QE, which is a work that Sofia Economou talked about a couple of days ago in this conference, where one iteratively chooses the fermionic operator to append to the circuit that empirically lowers the consumption. And although this leads to some depth overhead, they have modified the algorithm to make it more hardware friendly, and this update is known as qubit adapt QE, and I think it's very promising. And then on the other hand, one can think of some machine learning aided strategies, and it comes to evolutionary algorithms here, and in particular to the works of evolutionary BQE and multi-objective BQE, where in general one optimizes the structure by keeping a population of quantum circuits and randomly mutating them to minimize some consumption. Of course, this comes at the overhead that one needs to either have a very long sequential computation of all the quantum circuits, or keep a lot of quantum circuits in parallel. So what we propose in our work is to grow the ansatz as follows. So at each iteration, what we do is to consider the cost function and try to wait until the costs converge using the classical optimizers. So we begin from some initial ansatz and inspire on the Barrett-Bratov phenomena, which is due to random initialization of the parameters. What we do is to once the circuit is optimized, we append identity resolution blocks of either 1 or 2 qubit gates. So these have these forms where Z denotes the rotation around Z, X denotes the rotation around X axis. And this is the 1 qubit block. And this is the 2-qubit blocks. So notice that, for instance, if the rotations are 0, this compiles to identity, and also this one. So what we do is to once the cost function converge, try to get a longer, a more interesting ansatz by appending at the random position of the circuit these blocks. So once appended, we try to minimize a bit more this cost function, and then because we don't want the circuit to grow infinitely, what we do is to try to compress this circuit as much as possible. We do this by using some cost-preserving compression rules, which some of them I draw here. So importantly, this allows to smoothly navigate the hyperparameter, the architecture hyperspace. So at each iteration, our algorithm can either accept the new ansatz or go back to the previous one or the best one that has found so far. So I hope this is clear enough. And I'm going to present some results by using our algorithm for VQE. So our first result refers to a transfer field basic model where we have considered finding the ground state of this Hamiltonian. What we show in these plots is the energy that we achieve for either 4 or 8 qubits. And the errors are acceptable, and the relative errors are quite acceptable. So what I like to show here is the learning process, if you want, of this one of these points here. So what I depict here is above the energy of the ansatz, the energy of the circuit that our algorithm proposed as the iterations evolve through time. And what we see is that the algorithm converges to some ansatz whose state is close to the ground state. And below, what I show is the circuit structure as the time evolves. And in this color that I think it's magenta, I'm colorblind, and I realize I don't. I put the color in the X format, but I don't know the name here. So let's say this is magenta and this is gray. The trainable parameters are gray, and this is the magenta, the C-nodes. I show the number of C-nodes that we get as a function of time, and the number of trainable parameters that we get. And what we see is that this is comparable to the so taking a hardware efficient ansatz with the same number of either trainable parameters or the same number of C-nodes, we even get a lower energy, which is promising, in particular for scenarios where we may have a noise. So some propaganda, we had to name our algorithm somehow, and we have termed it bands because it's variable ansatz. And this reminds to some skater shoes, which are quite popular nowadays. So next, we have considered the hydrogen molecule as it has been considered in the previous talk, and in general, this chemical Hamiltonian can be written in the second quantization as this the sum of terms where these H are the 1 and 2 electron overlap integrals that can be computed using these quantum chemistry methods. So again, what we show is how many iterations it demands the algorithm to converge to something close to the ground state, and something close here is something below chemical accuracy, which is some value down to which you can't discriminate nothing in quantum chemistry or chemistry in general. So what we have done next, and with this slide, I think I have 70 minutes, but this is the very last slide. We have shown more. So with what we have done here is to take this information that we have learned by using our algorithm and try to squeeze all this quantum information of the state that our algorithm prepares. So to squeeze it in as in fewer qubits, and this is done by using this quantum autoencoder idea that was proposed by Alan Aspuru, I think in 2017. And so what we want to learn now is an ansatz that an encoding that compresses the circuit into say, instead of having 4 qubits, only 2 qubits. So then we decode and we get a quantum state which is close to the ground state. And what I plot here is the energy that we get by using this autoencoder. So I have considered some training points which I show in blue. And then what we do is to use the very same encoding and decoding strategy to get the ground state of unseen molecules. And this is as a function of the bond length, so for unseen bonds, if you want. And okay, this we get this. Importantly, of course, we have used this. We have found our ansatz by using our algorithm, sure. And what we see is that the cost function decreases. So with this, what we want to somehow push forward a lot for is to encourage people to use variable structure ansatz, not only in doing VQE, but for quantum machine learning purposes in general. So there are a lot of extensions that we can do of our algorithm, and for sure we can think on smarter ways to select gates at each instance of the process, like using some very powerful AI decision maker. But for the moment, it's fine. And then we can also think of using some more efficient way to compress the circuit. And there has been some proposals using ZX calculus. I have a typo here. So with this, I think it's time to finish. And well, thank you very much for your attention.
Thank you, Matias, for the talk. So I think we have time for a few questions. So please raise your hands or type the question in the Q&A section. Okay, in the meantime, I can ask for a question. So when you introduced the compression part in your algorithm, so I didn't get exactly how the compression works there. So I think it is ansatz dependent. Is that right?
Sure. So what we do is to scan the ansatz. So what we do is to scan all the circuit, okay? And for instance, if the new proposal, so if this circuit has, for instance, say 2 rotations that are in parallel, so you have a set rotation and then a set rotation, you just add those values, right? Mm-hmm. Or for instance, the mutation of the algorithm may lead to having 2 consecutive C nodes, and this compiles to into the identity. So we erase it. Okay.
Mm-hmm.
So these are the kind of rules that we apply. And also, for instance, if you have more than 3 consecutive single qubit rotations, or you can compress them with only 3. And then what we also do is to also scan, to compute the cost function for a circuit that misses only 1 qubit unitary. So if this so for each unitary in the circuit, we delete it and compute the cost function. And if the cost function is not increased too much, we take it out from the circuit.
Okay, so just to see whether I understood correctly, so if I look at the second circuit from the top right, so as far as I understand, so if it happens that the parameters in those Z, X, and Z gates, no, I mean the one in the gray block.
So for instance, here we have 4 consecutive rotations, and they have been compiled into 3.
Mm-hmm.
Right. And for instance, here we have 2 consecutive C-nodes, and they have been compiled to entity.
Mm-hmm. I see. But can't you just, I mean, remove them from the beginning, or so?
Oh, yeah, this is schematic. Okay, so maybe we have more gates here. Maybe it's.
Mm-hmm.
Okay. Was that what you meant?
No, I meant I don't know. If you look at the second circuit from the top right, no. Okay. I see. So the issue is the following: that due to our mechanism of erasing single qubit unitaries, if they are not very necessary to decrease the cost, one may delete 1 or more single qubit unitaries, and then these circuits may be allowed for simplification. Mm-hmm.
Okay.
I see. So I also guess that when the parameters are very close to 0, those gates are close to 1, I guess, and you can also remove them. Or do you do also something like this, or? Or do you expect some possible compression in this way?
Sure. So in case they are close to 0, then this will be reflected on the cost value function. For the case they are not in the circuit, and then for sure we will be removing them. Mm-hmm. So the answer will be yes. Okay. I mean, not explicitly we check what the value is, but rather to check how the cost function behaves as a function of that rotation.
Mm-hmm. Okay, thank you. So are there other questions? I can't see any raised hands. So last time to raise your hands. Okay, so if there are no questions, then we can also thank the speaker and move to the next talk. So thank you, Matias.
Welcome.
So hi, Bryce.
Hello, thank you. Sorry, give me one moment to share my screen.
Yeah, so it's a pleasure to introduce Bryce Fuller from IBM Quantum in the USA, right? And so he will talk about accurate simulation of quantum chemistry on quantum computers integrated via neural networks. So let's see whether I still can't see the screen.
Yeah, sorry, it suddenly made me go turn on permissions for something, but I should be good now.
Yeah, sure.
Can you see my screen?
Well, I can see something. Okay, so yes, now yes.
Okay, great.
Perfect. Okay.
Thank you for the introduction. I have a lot to get through, so I'm going to get started. I do want to mention this is joint work between myself and the authors listed below. Great. So the rough agenda for what I want to cover, I'm going to quickly motivate what I would call the variance problem in near-term quantum chemistry. Talk about how neural network estimators were introduced previously to address this, and then toward the end of the talk, we will cover what me and my collaborators are working on now, which is using an extension of neural network estimators to actually mitigate noise on noisy quantum states. Great. So for a quick recap for those who may not be directly familiar, typically in near-term quantum chemistry, you have some trial state psi on a quantum computer. You're interested in evaluating its energy with respect to some Hamiltonian, and you're often looking for the ground state. Right? So we know that as we approach the ground state, we should expect our variance of our estimator to go to 0, sort of intuitively. However, in practice, this isn't actually what happens, right? Because you can't really rotate directly into the eigenbasis of your Hamiltonian. And so what we do in practice is we would actually decompose our Hamiltonian as a weighted sum of Pauli operators, right? And this has the nice property that we know how to measure all of these Pauli operators. And so we can evaluate this expression just by a linearity and knowing this decomposition, right? However, you lose this zero variance property when you do this, right? Because this trial state, this ground state you're looking for is highly unlikely to be an eigenstate of all of these Pauli observables, right? So you can actually relate the coefficients in this decomposition as well as the variance of each Pauli string to the number of shots you need to get within a specific error, right? And I know I'm moving quickly, but this issue is noticed by Matias Bilkis and others. This is the first work I'm aware of that talked about this, but you can do sort of a back of the napkin calculation and say, if I need to estimate a certain molecule's energy within a particular error, what is an upper bound on the number of shots that I would expect to need, right? And so if you do that, you quickly get extremely large numbers for molecules that maybe don't seem completely out of reach, but 100 trillion measurements is a lot, no matter how quick your quantum clock speed is, right? So it is worth pointing out that this is an upper bound, but this issue does arise experimentally, right? So the variance problem is essentially asking how can we massage our problem such that we can actually minimize the number of measurements we need to make to quantum hardware in order to get a reasonable answer. Okay. So I want to briefly cover a couple of strategies that are used in practice and proposed to address this problem, right? Just so that I can give some context for the neural network estimators approach, right? So one you would call Pauli grouping, right? You might observe that a lot of these Pauli strings that you need to evaluate actually commute with each other and can therefore be evaluated simultaneously. So you can do this pre-processing step of sort of grouping all of your observables into these sets. And then evaluate each set at once, right? Just by doing some post-processing on those measurements. And empirically, you can get about an order of magnitude reduction in the number of shots you need, right? There's of course a lot of details here that I'm not covering. If you want to do this properly, you should probably be concerned about the covariances between your observables, but I'm not going to get too much into that. Right? As another point of reference, this technique that was proposed in this paper down here by Huggins et al. But the idea is that you can essentially rewrite your Hamiltonian such that there's a linear number of terms that you need to evaluate on hardware, and each of them comes with a linear depth change of basis circuit, right? So this might be something that you're interested in doing if you can afford the extra depth in your circuits at this time, right? This third technique that we're going to spend much more time talking about is substantially different, right? So the idea is that we're actually going to integrate a neural network into this model such that we can sort of learn the underlying distribution of measurement statistics and then evaluate our Hamiltonian directly on this neural network representation, right? So this is what we're going to be focusing on for the remainder of the talk. Great. So I will go through more details about this neural network estimator, but I wanted to briefly just sort of cover the high level algorithm sketch. What are the steps that we're going to be going through here? So the first two are very similar to what you would do in a regular, maybe VQE setting. You prepare your quantum state, often a trial state, or if it's near the end, it's an approximation of your ground state. Take a bunch of measurements in the bases given by your decomposition. However, in step 3, instead of using these to directly compute our energy, we're actually going to kind of regard them as a data set of sample basis pairs, right? You can actually write this a little more succinctly in this notation down here. So sigma is going to correspond to one of these configurations, which encodes both the basis and the observation that you received. Great. Once you have this data set, you can then train a restricted Boltzmann machine to try and reproduce the measurement statistics that you observe in that data set via unsupervised learning, right? So down here, I've reproduced the familiar equation of a restricted Boltzmann machine, but notably, we're going to require that this model produces complex outputs, right? We want to be able to query specific amplitudes of our model. So these are going to be complex valued weights down here now. But great. And then finally, once you have this model, you can then draw samples from your neural network directly. And if you were successful, then you shouldn't really be able to distinguish those very well from having drawn a sample off of your quantum computer. And you can use those samples to evaluate your Hamiltonian's energy. And this process would be much faster than evaluating it on quantum hardware, just because drawing samples classically is much more efficient at the moment, at least. Great. So I want to very quickly sort of run through some of the objections that I hear sometimes whenever discussing these things. I would say they're reasonable objections at first, so that's why I want to address them, right? But you might have seen that previous slide that said, that shouldn't work. It's going to take exponential measurements to perform tomography, right? And that's true, but that's not really the situation that we're in, because we're not performing full tomography. Notably, we only care that our Hamiltonian, our state produces the same statistics on a very specific set of observables, right? We're not going to be performing general measurements on this neural network quantum state. And moreover, when our target state is actually near the ground state, these expectations of these Pauli observables actually fully constrain the pure state that we could be modeling, right? So we don't have this guarantee during training, but you could say it's heuristically a nice thing to have, right? Another thing is you might be tempted to say, if you can model this state classically at the end, which is not a given, by the way, there's certainly some systematic bias that occurs there. Why involve the quantum computer in the first place? Why not just be using these neural network models directly, right? And I would say the short answer is that the state being easy to model does not imply it's easy to find, right? This picture I'm not going to have a lot of time to dwell on, but this blue region, or the striped region rather, is corresponding to the state of the region of Hilbert space of states that are maybe easily modelable. And so it's very possible that there's a connected path between whatever your initial state is and wherever you want to go, but that path could be much more difficult to navigate than, say, a more direct path that a VQE circuit could take. So that's what this dotted line is representing, that you're doing your state preparation on a quantum computer and then measuring after you've already kind of crossed this gulf, right? So intuitively, this is kind of the idea as to why this might still be useful, right? Okay, so on this slide, I just wanted to sort of briefly show a picture of what this architecture might look like, right? So I think this is a very familiar picture to most people. You would have this gray region is just some general quantum circuit, right? And this is indicating that we are measuring in a restricted set of bases, right? Just these local Pauli observables. And then this last block saying that we're taking all of those measurements and now feeding them into a classical model, right? A restricted Boltzmann machine in this case. And again, our goal is to learn a set of parameters, which I've denoted just this lambda shorthand, such that the measurement statistics that we observe from our quantum computer are very similar to those that we would see on our neural network, right? So let's look at this expression, right? This is saying that if we query our quantum or our neural network representation with a particular configuration, we're going to get back a complex number, and we would hope that the amplitude or the magnitude squared of that number, is proportional, or is equal to this probability of measuring it in our actual system in that exact basis, right? So all this is to say that we want our model to reproduce the measurement statistics in our data set, right? And KL divergence is a natural cost function for this, right? We want these two distributions to coincide, right? Okay. So again, this is still covering neural network estimators. This is older results, but What this picture is showing is essentially, we would expect that your neural network will incur some bias, some systematic bias, right? But the variational principle does still apply. So you can still consider the energy estimates you get out as upper bounds, right? But what this picture is showing is really the bias variance trade-off that you're incurring, right? So you can see this little red window here corresponds to the window of chemical accuracy. This sloping distribution is the distribution of energy values you might reach using maybe just the standard like direct measurement or direct averaging is what I would call it. And these histograms correspond to the energy measurements obtained through using one of these RBM estimators, right? So you can see that they do incur a bias, but this variance trade-off is so great that it still falls within chemical accuracy, right? So great. And then another figure from same paper, just cited down here. This is showing on the y-axis for each of the same molecules, the probability of reaching chemical accuracy as a function of the number of measurements used, right? So this dashed line being this upper bound that we mentioned earlier, this solid line being what is actually observed whenever you take into account the variances of each of those estimators, and then this dotted line over here corresponding to using this neural network estimator in conjunction with a quantum computer. So you can see several orders of magnitude improvement for the problems tried here. So this is encouraging. Okay, so now I want to move on to how you would generalize this to not just target pure states, right? So you might wonder what would happen if you applied a model like this to hardware, and you might worry that it may not converge if it can't model the actual underlying mixed state properly, right? So the solution to this is you can actually add additional hidden units to your restricted Boltzmann machine. And then essentially you're tracing out over those units in a special way that I won't have time to sort of detail in this talk. But the upshot is that you get an expression like this down here, where you now have two indices to probe your configuration with, or probe your two configurations, excuse me, to probe your mixed state with. And these sort of parameterize a density matrix for you, right? Where this expression down here is encoding this sort of mixed state. Note that these psi a's are not inherently normalized, so their relative magnitudes encode the relative weights of this decomposition here. Okay. So on this plot, I'm just showing some early data for these trained mixed neural networks, right? So this is trained on a noisy lithium hydride ground state on 4 qubits, right? And so, when this noise model here is at 0, right? To be clear, this noise model is depolarizing noise of various strengths on each single and 2 qubit gate multiplied by some constant, and that constant is this x-axis. So what's shown here is essentially the difference in energy that our neural network model achieved versus the exact noisy energy that it was trying to target. And this blue curve up at the top is essentially showing the standard deviation of the error we would expect by just taking the naive approach and using our data set to directly compute these expectation values. So the goal would be that each of these lines beat this curve. I won't have time to go into too much detail about these dashed and dotted lines. I think you can just ignore them and consider the straight ones for the moment out of time. But again, these colors are representing various ancilla qubits. So one thing that's not abundantly clear from this picture is what is the value of increasing to larger numbers of ancillas, right? I mean, I guess you could say that this red curve seems like it's kind of winning out on the bottom as we get into noisier regions, but it's not really super compelling. So you might want to probe like what is actually the value of adding more of these ancillas. So in that line of thinking, we would expect that this target state that we're actually trying to learn, we would hope it's approximately low rank, which is equivalent to saying that it hasn't been completely dominated by noise, right? We would hope that the dominant pure state in our target state is this sort of ideal state, right? And since in this case we are targeting noisy ground states, we would hope that it would have very high overlap with the ground state, right? So as a sanity check, one thing you might want to see is that if you were to take one of these neural network models, these quantum neural network states, and diagonalize it and keep this principal eigenvector, you would hope that the ground state would be very close to that principal eigenvector, right? And so this is something that we did, right? So this is the same data showed before, except now it's not a difference in energy, it's just the absolute scale, right? So each of these solid curves is the one pictured before, and there's now a black curve in here. So before we were measuring distances between these colored curves and this black curve, right? And what I've put it in absolute terms now because you can see the ground state down here, and each of these dashed lines is now corresponding to this procedure of diagonalizing the density matrix we get from our neural network, keeping the principal eigenvector and computing its energy, right? And so in this picture, it's much more clear what the impact of adding more ancilla qubits is, right? You see a really dramatic reduction in the error, right? So, you know, this was pretty remarkable to me, at least, just because, you know, even a reasonably large amount of noise shows that our neural network is sort of understanding that the dominant eigenvector is indeed very close to the ground state. So I thought this was encouraging. So one observation is that you know, after you've sort of trained your model, not only do you have this nice compact representation of your state, you actually have new types of sampling access, unphysical types of sampling access to the state. So in particular, you can query particular elements, and you can also sample particular elements of rho according to different norms, right? And so this has to do with the details of how the Metropolis Hastings algorithms is operating under the hood, right? Again, won't have time to get too far into that, but you know, these are new types of resources that you have at your disposal once you have this trained state. And so the goal of me and my collaborators is to see whether these can be used for noise reduction, right? And this sort of sanity check I just showed before could be viewed as a form of sort of naive or maybe unscalable noise reduction, right? Where we use this query access to, you know, query every element of our density matrix. We brute force diagonalized it, so to speak, and then just, you know, return the energy of the principal eigenvector in not really any scalable way. But the goal of the remainder of this talk is to convince you that, or to give you an idea rather of how me and my collaborators are hoping to make this efficient, right? So I want to sketch the high level ideas behind this. How am I doing on time, by the way?
I think it's roughly 17 minutes.
Okay, I'll wrap it up very quickly then.
Yeah.
So the idea behind this, right, is that you want to define some cost function, which I've labeled C of phi over here, which is defined as follows. You can convince yourself that this cost function is maximized whenever our target state, whenever psi is this principal component of our density matrix, right? From here, we're going to decompose psi in this basis of purified states, right? So these A are indexing our ancilla variables. I don't have a lot of time to explain more about what this means, but so I guess look out for the paper, right? But when you make this substitution and reorganize all your indices, you can actually rewrite this expression as a function like this over here, where C is an m-dimensional complex vector, where m is the number of ancillas we have, and m and b are both m by m matrices as well, right? So these are all going to be maybe at most order of the number of qubits dimensions that you have. So we would expect these to be manageable, right? And importantly, these M and B matrices can be estimated using the sampling access that I was referring to before. So each of these particular quantities is estimatable, right? And you know, it's worth noting that these are estimated via Monte Carlo sampling. So this is why, you know, this technique would be considered heuristic. But you know, we would expect this to work well for some problems of interest, right? Finally, once you have these M and B matrices, you can solve the equation on the previous page for C, right? Recall that C was this these were the coefficients in our decomposition of psi. And so now we can actually evaluate our energy of our ground state, our principal component just by using the linearity, right? And so this is sort of the quick idea of how you can use this sort of non-physical sampling access to heuristically try and learn the energy of this principal component of your mixed state, right? So I would say the conclusions of this, right, are for one, the neural network estimators are an interesting tool, and that people should consider using them as a way to address this variance problem. It's also very nice that everything happens in post-processing, right? I mean, it's very interesting to be able to do noise reduction on quantum measurements that I got from someone that, you know, happened several years ago. And also this idea of having a classical representation of your state that gives you non-physical sampling access, I think is perhaps more general than just the situation in which we're applying it, right? So just recently, one of my collaborators came up with the idea that you could actually swap out the RBM in this model for a tensor network model and use similar kind of ideas from that field. So I think this kind of opens the door to asking, what can we really do with these types of sampling access if we can get them? And how can that be used to sort of reduce noise in near-term quantum computations? So I know I'm over time, but with that, I will turn it over. And I do want to give a huge shout out to all my collaborators. This is certainly not work done in isolation. With that, I'll turn it over to questions.
Thank you. So thanks a lot for the talk. So we have time for a few questions.
Great.
So please raise your hands or write your questions in the Q&A section.
I can no longer see the Q&A box.
Oh, I can see that.
I'm not sure where mine went.
Well, it's in the center bottom of my screen.
Maybe it's because I'm presenting still.
Okay, so if there are no, so while we wait for other questions, I can also ask a question.
Yes, please.
So perhaps you said that, but okay, so no, wait, there is a question. Okay, no,
Oh, I see. Okay.
So, perhaps you said this, but it was not particularly clear to me. So based on your experience, when do you think that this method can be applied? So does the Hamiltonian need to satisfy, I don't know, does it apply to gapped systems or Hamiltonians with lowly entangled ground state? I mean, are there limitations like this or no?
That's a good question. I'm not the chemistry expert on this project, so I worry that if I speculate that it wouldn't be a valuable answer. But I think that these techniques need to be tried more and to see how well they work as we try and scale them up, right? I think that's still sort of an open question as to how well these neural network models will actually be able to represent these states that are of interest. I guess that's the core of your question, is how much systematic error should we really expect? I don't have a good answer to that, unfortunately.
Okay, so this is not so this is still an open problem for this sort of neural network states.
As far as yes, I believe so. So maybe if there's work that that's pushed this boundary, much further than I've yet to become aware of it.
Okay. So any more questions from the audience? Okay, so if not, let's thank Bryce again. And so this concludes this this session. So the next one will start in around 20 minutes, I think. So thank you all. I want to thank all the speakers. Thank you.
Much appreciated.